This will be a presentation to get a handle on the ideas of emission and absorption spectra. You can see here pictures of what the two might look like for hydrogen. You can see the emission spectrum is a black field with colors imposed on it. Those colors are the lights that hydrogen gives off. So if you had somehow something that was only generating a hydrogen spectrum, these are the spectral lines you would see in the emission spectrum. Below that is an absorption spectrum. It's a complete rainbow with colors, those of the hydrogen spectrum, subtracted from it. That's what an absorption spectrum looks like. So let's learn about how those things can be produced. This is a sketch showing thermal radiation spectra. This is also called Blackbody spectra for objects at 3 different temperatures. All of these are plotted using the theoretical formula for perfect emitters. Most objects in nature don't behave quite this perfectly, but there are a few examples of nearly perfect black bodies in nature, as well as a few things, such as stars, that produce curves close enough to the perfect shape so that we can measure their temperatures using Venns' law. This shows a classic method for looking at the spectrum of an object. You take the collection of light coming off of an object, have it pass through a slit so you have a narrow beam of light, then let it pass through a prism. The light will be separated into separate colors by the prism through a property called dispersion. We won't worry about that here. White light will produce a nice rainbow effect when you do this. If you can somehow also get information on how much power is delivered at each wavelength, you can trace out the thermal radiation curve on a graph, and you could determine the temperature of the object that produced the light. That would be using Venns' law. Now we're looking at the emission spectra of several different types of atoms. One feature of these emission spectra is that every type of atom produces its own set of spectral lines. They're called spectral lines because the instrument used to view them splits the mixture of light, so that when viewing the light through a viewpoint in the instrument, you see vertical lines. To understand how these are produced, we need to know about some properties of atoms. If you're going to carry a picture of an atom around in your head, this energy level diagram is the one to have. This shows the energy levels for the hydrogen atom. Every element will have a different set of energy levels. When an electron is in what is called an excited state, it will be in an energy level above the ground state. This is the ground state down here. Any of the states above here are excited states. Most of the time the electron will be in the ground state, but if you add energy to the atom in some way, the electron can rise up. If the electron returns to the ground state from an excited state, it will emit or give off the energy it's lost, and that energy is carried away in a photon, which is a particle of light. The photon behaves as both a particle and a wave. That's one of the more mysterious things about how nature behaves. You may notice that the arrows showing those transitions for the electrons point both up and down. There's an arrow at each end of it. This is because it's possible for an electron to be excited to a higher energy level if it absorbs just the right amount of energy. From the ground state of 0 electron volts, the electron would need exactly 10.2 electron volts to come up to this first excited state. To go from the first excited state to the 12.1 electron volt energy level, it would need exactly 1.9 electron volts. Not give it enough, and the energy, the photon, will pass right by the atom. A photon with the same energy that the electron has when it drops down between 2 levels can cause an electron to jump up to that higher level. It's important to realize that a spectrum is not produced by a single atom. You get a spectrum when you have a collection of a large number of atoms that will get excited and give off light. Then some of the atoms will produce each of the different transitions, and you end up with a collection of all the different energies of photons. Each energy has a different wavelength or color of light, and that's how you get the spectrum. It's not hard to get a large number of atoms. The air in the room you're in has more than 1,000,000,000,000,000 molecules in each cubic centimeter, actually about 24 million kilometers, and a cubic centimeter is only about the volume of the end of your little finger. This shows an absorption spectrum for hydrogen, and the bottom curve there shows the effect that the absorption lines have on a thermal radiation spectrum. On a thermal radiation curve, the absorption of particular wavelengths of light causes a dip in the curve, places of low energy. Here's a way that it might be produced. You start with something that will produce a continuous spectrum, a nice smooth thermal radiation curve. Then if the light from that, if you shine it through a prism or something, you would get a continuous spectrum, a nice complete rainbow with no black lines in there. However, if you take that light, the continuous spectrum, and pass it through a cloud of gas, the particles in the gas cloud will absorb their particular wavelengths of light. And when the light gets through the cloud of gas, you'll have a continuous spectrum with dark lines. Those are places where the spectrum, the light, has been diminished at particular wavelengths. And which wavelengths are diminished depends on which atoms you have in that cloud of dust. Something interesting is that if you could view that cloud of gas from the side, you'd see a bright line spectrum coming out of it. Every time an atom in the cloud of gas absorbs energy and an electron gets excited, it will de-excite, the atom will, and give off a photon, but those photons go in every direction. They don't necessarily go in the original direction. That's why it's diminished when it comes out of there. But if you view it from off to the side, you can see an emission spectrum. Here's a real world curve. This is the actual spectrum for a star. I don't think this is the sun, but I don't know for sure what this happens to be. But you can see all kinds of dips in this curve. One thing you can see is that it does roughly trace out a thermal radiation spectrum, but it has zillions of dips in here, and you can measure the wavelengths of those dips very carefully and find out what element it was that absorbed the light that produced that dip, that little absorption line. And you can see how the dips in this correspond to dark lines up above. Sodium, Na, this would be at about 589 nanometers. The units on the bottom here are angstroms, not nanometers. So they're 10 times higher than the number of nanometers. But you can see different absorption lines up here caused by different elements. And there are actually a couple of molecules down here. O2, that's an oxygen molecule with 2 oxygen atoms in it. This is a picture of a small part of the sun spectrum. This only goes from 530.5 nanometers, or actually about 530 nanometers over on the far left end, up to a little more than 532 nanometers. Again, the top scale is in angstroms. Divide it by 10 and you'll have the scale in nanometers. Something to notice, though, is in that tiny section of the visible spectrum, which, by the way, this would look green, and if you compared the left end to the right end with your eyes looking at the color, you probably wouldn't be able to tell any difference between the two. It would all appear to be the same shade of green. But an instrument can measure these wavelengths carefully and see all of these absorption lines. But look at all of these things. Iron, that's Fe. Iron, Fe again. Iron, iron, iron all over the place. And then there's also some chromium in here. And let's see, SC scandium, I think, and I can't remember what ND happens to be. And Y is probably one of the elements named after the place in Sweden where erbium and ytterbium come from. And there are several elements named from one place. Anyway, look at all those things in a tiny section, those little tiny absorption lines in there. By the way, at one time, astronomers thought that the sun was made of iron because of all the iron absorption lines in the spectrum from the sun. Turns out iron has a whole lot of transitions in the electron levels that will produce visible spectral lines, but there isn't that much iron in the sun. Turns out the sun is 3/4 hydrogen, 1/4 helium, and traces of everything else. The iron is just a trace element, but because it has many absorption lines and emission lines in the visible part of the spectrum, that's why we happen to see this. Here's the actual solar spectrum, and it's spread out over a whole bunch of rows. To see this correctly, you'd have to print this off on colored paper, get a pair of scissors, and snip out each one of the rows that you have here. And then when you get to the right end of the bottom row, you tape down the left end of the next row up. When you get to the end of that row, then you'd tape the right end of the next row up, or the left end of the next row up, and so forth, and you'd get a very long spectrum. But look at all the absorption lines in the light from the sun, all kinds of things. By the way, where you see these kind of wide fuzzy ones, those are often molecular absorption lines, things like the O2 that we saw in the sun's atmosphere. So things like that occur there. But those are all absorption lines. I hope you have a better understanding now of what an absorption spectrum is and what an emission spectrum is.